Okay, so in the last video and in class, we've talked repeatedly about sequences and properties of sequences, things like boundedness and monotone. And now we're going to transition over to series. Again, remember the difference is I can have a sequence, say the sequence a sub n equals 1 over n, which is 1, 1/2, 1/3, and so on. We call it the harmonic series, the harmonic sequence in class. Then I can look at the series 1 over n, where I add up the terms there, which is 1 plus 1/2 plus 1/3 plus so on and so forth. And the question with series is, does that series converge or diverge? When I add up all the terms, does it add up to a number or does it shoot off to infinity? And now we have to start looking at different tricks we can use to actually determine if that thing converges or diverges. And one thing I will point out, and I mentioned this in class briefly, a lot of times, say, we've already looked at some series. Suppose I have the series 1 over 2 to the n equals 1 to infinity. We looked at this in class. Well, that's 1/2 plus 1/4 plus 1/8 and so on. That one's geometric. The ratio is 1/2, which is less than 1. So then we said in class the sum is the first term over 1 minus the ratio. 1/2 over 1 minus 1/2, that's 1/2 over 1/2, and I get 1. In class we altered it slightly and got 2, but it doesn't matter. Point is, we showed that this geometric series converges, and we have a formula we can actually use to determine what it converges to. That works for geometric series, and it works for a few others that we'll look at, but in general, you really can't do that. For most of the series we look at, we'll never actually figure out what they add up to, because we really can't. And we'll see why later on. But the best we'll be able to do for a given series is, does it converge or diverge? Hey, this one's geometric, it converges. Hey, this one's harmonic, I don't actually know if it converges or diverges yet. But that's all we really do. And we'll spend the bulk of this chapter looking at different tricks, different tests, to determine if something converges or diverges. Today we're only going to look at maybe a special case of one type of series, maybe look at that harmonic one again, and then we'll develop our first test that we can use to see when things converge or diverge. So let's see. Suppose I have this series right here. N equals 1 to infinity, 1 over n minus 1 over n plus 1. I want to know if that converges or diverges. And as of right now, I don't even really know what that looks like. So one of the first things you can do to get an idea, at least as you're starting, is to draw out some of the terms of the series and see what you get and see if you can see something going on. So for this, I plug in n equal to 1, first term, and I get 1 over 1, which is 1, minus 1 over 2, 1/2, plus, then I plug in n equal to 2, I get 1 over 2 minus 1 over 3, plus, I plug in 3, I get 1 over 3 minus 1 over 4, plus, dot, 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 I think the last term would be 1 over n minus 1 over n plus 1. And then this would continue forever, but etc., etc., etc. There's a point there. If I kind of look at this, we said in class, one of the things I can do to see what's going on is to look at the sequence of partial sums. And just on the off chance you may have somewhat forgotten what that is, the sequence of partial sums, we call them S's. S sub 1 is the first sum, which is 1 minus 1/2, which I know is just 1/2. S sub 2 is the sum of the first two terms, which is 1 minus 1/2 plus 1/2 minus 1/3, which is 1 minus 1/2 plus 1/2, that cancels. It's 1 minus 1/3, which is 2/3. S sub 3 would be 1 minus 1/2 plus 1/2 minus 1/3 plus 1/3 minus 1/4. And if we kind of see the pattern here, now I have minus 1/2 plus 1/2 minus 1/3 plus 1/3. Those cancel. I get 1 minus 1/4, which is 3/4. And now if I generalize down to s sub n, well, it's what I have written up there. 1 minus a half, plus a half minus a third, plus a third minus a fourth, plus all the way out to the nth term, which is 1 over n minus 1 over n plus 1. But then clearly, minus a half plus a half cancels, minus a third plus a third cancels. I didn't write it, but there's a minus a fourth here. The next term will have a plus a fourth, and that'll cancel. This is a plus 1 over n. The previous term will have a minus 1 over n. That'll cancel, and s sub n will just be the first term 1 minus the last term 1 over n plus 1. And now, if you remember when we were talking about partial sums and sequences of partial sums, we said if the sequence of partial sums converges, then whatever it converges, then the series will converge, and whatever the sequence of partial sums converges to is the sum of the series. We had mentioned all that in class, so I don't want to rehash it all now. But clearly, this sequence of partial sums, s sub n, as n approaches infinity, that becomes 0, and I get 1 minus 0. So this approaches 1. Which then tells me, since the sequence of partial sums converges to 1, then the series itself converges to 1. And just looking at the first few terms, it's pretty obvious. A half, then I get 2/3, then I get 3/4. Keep in mind, these are sums. But yes, I'm adding on each time, but I'm always adding on and just getting closer and closer to 1. Next, if you look at the pattern, 1/2, 2/3, 3/4. My next sum would be 4/5, then 5/6, then 6/7, and so on. And I'll always be getting closer to 1, but anytime I stop to find one of the terms of the sequence here, I'll be less than 1, but the series goes off forever, so it'll just add up to 1. I know that takes a little bit of thought, so feel free to ponder it after you pause this video or finish watching the video. But as far as it goes, this is a special type of series. It's what's called a telescoping series. As to why they name it that, I don't actually know. I would assume it's because it's a simple thing here that telescopes out into this really big thing that doesn't actually matter because everything on the inside just cancels out and you're just left with what you started with. That's a guess. I don't actually know for sure. But that now means if we have a geometric series, then we know it converges if the ratio is less than 1, and we can figure out what the series converges to. If we have a telescoping series, meaning you can somehow manipulate it to make it look like this, there are different forms of this. But you'll see it if you plug in the first few terms, we'll see this cancellation going on. And if you can somehow show it's telescoping, then you can say, oh, it converges, and it should usually converge to the first term. So that gives us two types of series to work with. We've already mentioned the harmonic one, but as of yet, we still have absolutely no idea whether it converges or not. But now we can look at something else. So there is a theorem, and I keep checking the time on my iPad to see how long I can make this video because they're time limited. We can say this. That's a terrible symbol. If the series a sub n, if the limit of the a sub n's, limit as n approaches infinity of the a sub n's is unequal to 0. No, we're going to do this. I have two different theorems and I'm trying to decide which to do first. We'll start with this one. If the series of a sub n converges, then the limit as n approaches infinity of a sub n equals 0. We'll start with this one. So if a series converges, then the limit of the terms of the sequence that's generating the series has to be 0. We don't necessarily have to prove this. It should be pretty obvious. If I have some series, and we've mentioned this in class, both when we were talking about the calculus of improper integrals and just looking at a few sequences and basic series, if I'm going to add things infinitely, then the only way that infinite sum can approach a number that is in infinity is if the terms get smaller and smaller and smaller. Because if I have some series and maybe the sequence looks like this, even if the terms of that sequence are approaching 1, well, that means that eventually you're adding up 1 infinitely, which is going to give you infinity. The only way you can add an infinite number of things together and still end up with a number that is an infinity is if somehow your sequence gets really small, in particular, gets really small really fast. Again, we did this when looking at improper integrals and trying to determine how quickly different functions were approaching 0, which dictated if the improper integral converged or not. The same idea here. The only way a series can converge is if most of the terms are essentially 0, and they don't matter. If they're not 0, they do matter. You add them infinitely, you get infinity. So that should be pretty obvious. But since that is true, I don't know how many of you have taken logic, but if you've ever taken logic, there are different rules for logic. This is called the conditional statement, an if-then statement. When you deal with conditional statements, you can also have what's called the converse, the inverse, and the contrapositive. If you're going to end up doing a whole lot of math, you need to know these what these terms are and what they mean. If you're not, then you're kind of okay here. But there's a trick here in math that says if you have a conditional statement, it's equivalent to the contrapositive of the statement. Which means, since this is true, then the contrapositive of that statement has to be true. And again, if you don't know what the contrapositive is, don't worry. But what the contrapositive actually says is, you flip your conditional statement. This is if this, then that. You flip it, and you negate it. Which means the contrapositive of this is if this is not true. So if the limit as n approaches infinity of a sub n is unequal to 0, then this is not true. Which means the series doesn't converge, which means it diverges. Again, if you don't know what the contrapositive is, just trust me. You take a conditional, you flip it, and you negate both things. So now, since this is true, this also has to be true. If the limit as n approaches infinity of the terms of the sequence a sub n is unequal to 0, then the series diverges. This is actually an important test. It's called the nth term test for divergence. And essentially what we're going to do is, if we want to determine if a sequence converges or diverges, one thing we can do is throw it into this test. We can look at the terms of the sequence. If the limit of the terms of the sequence is unequal to 0, then we can immediately say the series diverges. Since we know rules for sequences now, it allows us to take a series, which we're still unfamiliar with, and think about it as a sequence, and then use the rules for sequences that we already know. One thing that is really important, that's called the nth term test for divergence, because it's a test for divergence. This does not say anything about convergence. It only says divergence, which means when we are doing all of these tests, this is the first one, we're going to do a lot more, we have to know the conditions of the test, and we have to apply it correctly and draw the correct conclusions. This is a test for divergence. The only conclusion you can get is divergence, because it's a test for divergence. You cannot get convergence as a conclusion, because that's not what this says right here. I'm just about out of time. Like I said, these videos on YouTube or whatever are time limited to 15 minutes. So I'm going to make one more video where I'll actually run through a few examples using this test so we can see how it works.